Okay, this is the third and maybe the final video on Chapter 5 about gases. Let's see, where I left off was I talked about pressure, volume, and temperature and the ideal gas law, the assumptions involved in that, and then a little bit about gas density. Next I want to talk about is partial pressure. So let's see, in any gas mixture, like let's take air for example. If I have a sample of air, it turns out the air is made up of many different components, and I hope I have a chance to talk about that, because near the end of the book it kind of talks about that, and there's some interesting things to discuss there. But for example, it has 78% of the air is nitrogen, 21% of the air is oxygen, and about 1% is something that most people don't know. Is there's actually 1%. You'd think, oh, is it carbon dioxide? You know, all this discussion about global warming and all that. No, it turns out 1% of our air is actually argon. Most people don't know that. So this, and then of course it has way less percentages of many other gases that we'll discuss later. Okay, so if in our sample here we actually had, let's say, 1 atmosphere pressure in this container of air, then the question you could ask, like, well, for this 1 atmosphere of pressure, how much of that pressure is related to the nitrogen gas, and how much of that pressure is caused by the oxygen gas, and how much is caused by the argon gas? Now, you might think, you know, who really cares? But this is definitely, but you'll see that there is a reason why this is important. But you can kind of think of this conceptually at a molecular level, is that we have all these gas molecules flying around in this container, bumping into the walls. So it's a valid question to say, well, how much of that pressure is caused by the nitrogen, how much is caused by the oxygen, and how much is caused by the argon? Well, it turns out that the amount of pressure caused by these three is directly related to the molar ratio of these gases. So for nitrogen, the pressure of nitrogen in this mixture is 0.78 atmospheres. Pressure of oxygen is 0.21 atmospheres. And the pressure of argon is 0.01 atmospheres. If you add up all these partial pressures, and that's what all these three things are the partial pressure associated with each of the compounds. When you add all these up, you'll see it comes out with 1 atmosphere, which is exactly what we measured. So partial pressure is just essentially a way of saying, which for a certain mixture of gas, how much of it really is nitrogen, how much of it is something else. Here's why this is interesting, and the only reason why I'm even spending any time on the video on this at all, is that in many gas mixtures that we encounter, we end up with X% of the gas that we're interested in. Doesn't matter what it is, but I'll basically say some gas like this, and then Y% of water. And the reason why we have water is that perhaps the way we've collected this gas involved actually the gas being collected over water. Okay, so now I wish I had drawn that a little bit better. So imagine that we actually have this vessel, and we've created some gas through some chemical reaction that's going on in water. So there's our water level. And that chemical reaction, let's say, is producing gas. So bubbles are coming up here, and we're making some gas that is, that's floating around in this gas, in this empty area above the liquid. Okay, obviously you can't see them, but I'm drawing in gas molecules, so I'm trying to. Now, in addition to the gas that we have produced by this reaction, we also have water gas, water vapor, that's up here as well. So in this gas mixture above the water line, there's going to be a certain, if we measure the whole pressure to be 1.0 atmospheres in this area, we can't basically say that this pressure is caused completely by this gas product that we've made in our reaction, because it's partially caused by the water that happens to be now the gaseous water that happens to be present kind of as like humidity in this same area above the water. So because of this, it just means that the pressure that we observe might be 1.0 atmospheres. But the pressure of the gas we're making and the pressure of the water are separate components that make up the total pressure. And the other, interesting fact is that for a given temperature that you're dealing with here, let's say this is room temperature, you can look up in a book. In fact, there's a table in your book, table 5.3, that lists the partial pressure of water at various temperatures. And at room temperature, it's roughly 22.4. It's roughly 22.4 divided by 760 atmospheres. So it's small, but it's not insignificant, and it needs to be taken into account, or else when you actually measure this pressure and you try to figure out how much gas did I make using the ideal gas law, you'll come up with the wrong number if you don't account for the fact that some of that pressure was due to water. Okay. All right. That was the only point I wanted to make there, because the book was a little, well, I don't know, maybe what wasn't as clear as maybe it could have been. Hopefully I've cleared that up. Okay. All right. Now I want to move on to, I mentioned early on that the ideal gas law equation, again, is a very convenient equation for letting us do some calculations based on some simple observations of temperature, pressure, and volume. But now I want to kind of talk about, and this is kind of a classic discussion of why in science a lot of times we make simplifying assumptions, because it allows us to make some progress. But it's always important to remember the assumptions you've made and to know when they don't apply. Okay, so I want to talk just a second about real gases, and it's more just to kind of illustrate the point that in science a lot of times we start with something simple, but then when we get into it a little bit deeper, we have to we have to turn the equation into something that's not as simple anymore to account for reality. Okay, so there's two things that are two big problems with the assumptions of the ideal gas law. And again, those assumptions, just to recap, is that the volume of the actual gas molecules themselves is insignificant compared to the volume of the vessel, and that when gas molecules fly around, they don't really encounter other gas molecules much, or those interactions are insignificant as compared with the interactions with the vessel's wall. Okay, so now this seems to work well when you have gases that aren't under pressure, that aren't under a lot of pressure, and so essentially gas molecules that can fly around have plenty of space, so the volumes are high. Now, with the volumes being high, the gas-to-gas molecule interactions are uncommon compared to the reactions with the vessel, and the actual volume that the gas takes up, the gas molecule itself takes up, is insignificant compared to the total volume. Okay, but as the volumes go down or as the pressures go up, these things fail. So it fails kind of in two ways. So now I have a vessel where I have a lot of gas molecules. Let's say it's under 100 atmospheres of pressure. So a lot of pressure. So here's two things that goes on. First of all, under this much pressure, the amount of volume you have for the amount of gas you have, the actual empty volume, or the vessel volume, is now kind of smaller as compared to the actual volume that takes up that the molecules themselves comprise. So essentially, that assumption that all of the volume of the vessel is available to the sizeless gas isn't such a good assumption anymore. And then secondly, and probably even more importantly, is when you get down to high pressure situations like this, the gas molecules are still flying around, fast, but now they're bumping in and having significant interactions with other gas molecules. So some of those collisions, instead of all those collisions impacting the wall or the sides of the vessel, imparting that pressure, now some of that is wasted or spent, maybe a better way of saying it, through interactions with between gas molecules. So essentially, taking that second reality first some of the pressure that we measure, the pressure we measure is essentially low by it's going to be a number that's off low by the factor of these wasted interactions. Okay, so if we were to measure pressure and want to do some sort of calculations with it, we need to adjust that number higher, because it should be higher. It should be higher than what we've measured. Okay. The second assumption, it has to do with the volume. We can measure the size of this volume and come up with some measurements of that volume, but in reality, all of that volume isn't really empty space or usable space by the gas, because some of that volume is actually consumed with the actual size of the gas molecules themselves. So the volume that we measure needs to actually be adjusted downward, lower, because what we measure is not the right number. It should be a little bit less. Okay, so when you look into the last section of the book, they talk about real gases. These two effects are accounted for, and in fact, they're actually they come up with a modified equation. I'm going to butcher it a bit, but it's essentially pressure times 1 plus some factor, the observed pressure, times 1 plus a factor, times the observed volume, times 1 minus a certain factor, equals nRT. So it kind of looks like our ideal gas law, but we adjust the observed pressure up to account for the interactions, essentially the lost pressure due to gas-to-gas interactions. And we adjust the observed volume down to account for the actual volume consumed by the molecules themselves. Okay, and then when you do that and you put in these, essentially they're almost like fudge factors that you put in here. When you do this, you get a bit of a more realistic equation for predicting, making predictions about the gases under these conditions that are maybe no longer, where the assumptions are of the ideal gas law don't apply. Okay. Okay. That's all I want to do there. I will end it. This one I'll spend just a second talking about the atmosphere. I'll do that in the last